It's actually kind of wild.
What's that?
The system dictating your massive cloud build this month, like the very first layer of the most advanced neural networks on Earth, it was actually invented back in 1994.
Yeah, and it wasn't even built for AI.
Exactly. It was designed to compress ZIP files.
It really puts things into perspective.
Yep.
When you realize that before a model does any like high-dimensional vector math or complex attention routing, it fundamentally relies on a text compression hack from the dial-up era.
Right, and that's the reality of the engineering stack we're dealing with here. Because when you're building an application, you wire up that API call, you send over a string of text, like a prompt or a massive block of messy JSON, and it just feels like the model reads it.
But it doesn't.
No, not at all. Under the hood, we aren't sending words to these models, we're sending arrays of integers. And the specific algorithm that translates your elegant string into those numbers, well, it dictates everything about how your application performs.
Oh, absolutely. It limits your context window. It changes how the model handles mathematical reasoning, and it determines your exact API latency.
Which is a huge deal.
Yeah. And for anyone pulling these APIs into production environments, treating that translation layer as a black box is just a massive liability. The way text is chopped up before it ever hits the embedding layer dictates the boundaries of what the model can actually, see.
Which is why tonight, for everyone tuning in, especially you software engineers building on top of these foundation models, we are stripping away the magic. We are taking a deep dive into the absolute bottom of the neural net stack.
Tokenization.
Specifically BytePair Encoding, or BPE, because this is the invisible engine powering GPT-4, Llama, Mistral, all of them. Okay, let's unpack this. Because to understand why modern AI behaves the way it does, we have to look at how a 90s compression algorithm became the industry standard for machine learning vocabularies.
The jump from shrinking file sizes to defining AI vocabularies actually makes perfect sense when you look at the underlying goal of both, which is finding the most efficient way to represent information.
Right.
BPE was never designed with natural language in mind. It doesn't know what a noun or a verb is. It purely looks for statistical efficiency.
I always think of it like refactoring code.
Oh, that's a good way to look at it.
Yeah, imagine you're auditing a massive legacy code base. You start noticing that these two specific lines of logic, let's call them line A and line B, they just keep appearing right next to each other, thousands of times across different files.
So you DRY it up. Don't repeat yourself.
Exactly. To save space and clean things up, you extract them, you wrap them into a single helper function, and you replace all those raw instances with your new function call. Your code base just got significantly shorter. BPE does that exact same iterative process, but with text sequences.
The mechanics of it are incredibly straightforward. It's a greedy, bottom-up algorithm. You start with the absolute smallest possible units, and you just iteratively merge the most frequent adjacent pairs until you hit a predefined target vocabulary size.
Let's actually walk through the example from our sources to lock this in. Imagine you have a tiny, isolated training data set.
Yeah.
Just 4 words. Low, lower, newest, and widest.
Okay.
And we have the frequencies of these words. Let's say low appears 5 times in the text, newest 6 times, and so on. We start by breaking everything down into a raw array of characters, LOWNEWEST.
And you also append a special marker, right? Like an underscore to the end of each word.
Right, exactly. So the algorithm knows where the word boundaries actually are.
So at this point, the algorithm does its first scan across the entire dataset and asks a purely statistical question. What 2 adjacent characters appear together most frequently?
And it looks at the counts for newest and widest and calculates that the character E and the character E sit next to each other 9 times. That's our highest frequency pair. Bam. It merges them. Nice.
Now, EAST is a brand new single token in our vocabulary.
Then it simply loops. It scans the data set again. It calculates that our brand new EAST token happens to sit directly to the left of T 9 times. So it merges those into EST.
And it just keeps looping. Eventually, it merges L and O into LU. If you run this while loop long enough on a massive corpus like common crawl, common prefixes and suffixes like est, or even entire common words, just becomes single, distinct tokens.
What's really fascinating here is the emergent property of this brute force counting. I mean, the algorithm discovers linguistic morphology entirely on its own.
Which is wild.
Yeah. We never provided a dictionary. We never hard-coded English grammar rules.
Yeah.
The system just noticed that the byte sequences for E, S, and T co-occur with overwhelming probability at the ends of character arrays, and it grouped them. It reverse engineers the structure of human language through sheer statistical force.
It's a brilliant mechanism, but there's a catch. We didn't stick with just characters.
No, we didn't. Because the internet isn't just ASCII text. If you want a model to read arbitrary digital data, you have to account for different alphabets, weird Unicode formatting, emojis, all of it.
Right. So starting around the GPT-2 era, engineers realized starting with characters was just too fragile. They dropped down to raw bytes. Every modern model starts with a base vocabulary of exactly 256 raw bytes.
Which makes sense on paper.
Byte-level BPE solves a massive out-of-vocabulary problem. If your base vocabulary is the 256 possible values of a byte, the concept of an unknown token completely vanishes.
Right, it can theoretically process anything.
Exactly. The model can fundamentally ingest any sequence of digital information, any language, any specialized mathematical symbol, even compiled binary executables or network packets. Everything is just constructed on top of those 256 foundational blocks.
But let me push back on this a bit, because as an engineer architecting a global application, dropping down to raw bytes introduces a pretty severe bottleneck when you factor in UTF-8 encoding.
Right. Variable width issue.
Yeah. In UTF-8, variable width encoding means a standard English character, like the letter A, is exactly 1 byte. But a single Chinese character or a Devanagari script character might require 3 or 4 bytes.
Right.
If the tokenizer runs its BPE training phase predominantly on an English-heavy dataset, it's going to aggressively merge those common English single bytes into massive, efficient word-level tokens. But those 3-byte Hindi characters...
They don't appear frequently enough in the training distribution to trigger the merge threshold.
Exactly. Wait, I mean, that's the core of the issue. The algorithm just leaves them shattered into individual raw byte tokens.
And if we connect this to the bigger picture, this variable width reality creates a steep multilingual tax that directly hits your cloud architecture.
Oh, absolutely.
An English word like transformer might compile down to a single token. A Hindi word of the exact same semantic meaning might remain decomposed as 6 separate byte tokens.
Think about the financial reality of that for a second. Imagine you launch your app in Mumbai tomorrow. Your users are inputting the exact same amount of semantic information as your US users. But because those Hindi strings decompose into so many more tokens, your API context window fills up 6 times faster.
Yeah.
Each token inherently carries less semantic weight for the model to attend to. And because OpenAI and Anthropic bill by the token, your operational costs just skyrocketed purely based on the language of the prompt.
A 1994 compression technique dictates your 2026 API billing model. It's a stark reminder that infrastructure choices always have downstream application costs.
So if standard BPE leaves us with these heavily skewed token counts, what are the architectural alternatives? Because the source and dig into how Google handles this with models like BERT and P5, they utilize systems like WordPiece and Unigram. And just to clarify, a common point of confusion for developers really quick. Sentence piece isn't a replacement algorithm. It's effectively a text processing wrapper that replaces spaces with an underscore-like character before tokenization, which is crucial for handling languages that don't use spaces, like Japanese.
Yeah, that's a good distinction to make.
But WordPiece, which powers BERT, actually fundamentally changes the merge logic.
It does. WordPiece makes a subtle but profound mathematical shift. BPE is entirely greedy, right? It merges the pair with the highest raw occurrence count. WordPiece uses pointwise mutual information, or PMI.
Okay, what does that actually mean in practice?
Instead of asking what pair occurs most often, it asks what pair occurs together much more often than we would expect them to, given their individual frequencies.
Okay, let's ground that concept. Think about the letters Q and U.
That's the perfect illustration. The letter Q is quite rare in the dataset. The letter U is relatively common. But mathematically, when you do see a Q, the probability that a U is sitting right next to it is massive. BPE might prioritize merging T and H just because TH has an astronomical raw count. But WordPiece calculates the PMI and realizes that Q and U are highly dependent on each other, scoring that merge significantly higher. It tends to capture linguistic units and root words a bit more naturally, breaking words apart into more logical morphological pieces.
And you can always spot a WordPiece tokenizer in the wild because it uses those double hash marks, #tag, to denote that a token is a continuation of a previous word.
Exactly.
But then there's Google's other approach, Unigram, and this completely flips the architecture. BPE and WordPiece are bottom-up algorithms. They build the vocabulary by merging. Unigram is a top-down approach.
Yep.
It initializes with a massive bloated vocabulary, say 500,000 tokens, and then ruthlessly prunes the lowest scoring tokens until it hits the target size.
And the mechanism it uses to score those tokens is probabilistic.
Which raises a major question for me, because the sources highlight that Unigram tokenizes probabilistically, meaning a complex word like internationalization, could be sliced into tokens multiple different valid ways during training.
Yeah, it could.
As a developer, introducing randomness into the tokenization layer of a deterministic system sounds like absolute chaos. Why would you ever want your input pipeline to be non-deterministic?
It definitely feels counterintuitive to anyone used to strict data pipelines. But in the context of training a neural network, that probabilistic splitting acts as an incredibly powerful form of built-in data augmentation.
Oh, interesting.
Yeah. If the model only ever sees internationalization chunked one rigid way, its internal representation becomes brittle. It overfits to that specific token sequence.
Ah, so if Unigram probabilistically feeds the model internationalization in one epoch and internationalization in the next, you're forcing the attention heads to map the underlying semantic meaning regardless of the specific token boundaries.
Exactly. It serves the same purpose as jittering or cropping images when training a computer vision model. By slightly altering the input representation, you force the network to learn a more robust, generalized understanding of the data. Models like T5 and MBART rely heavily on this unigram regularization.
That makes total sense from a training perspective. So we've got these different tokenizer philosophies. Let's look at how the actual size of the resulting vocabulary dictates the behavior of the models we interact with.
This is a fun one.
Take a standard string. The transformer architecture revolutionized NLP. Run that through the old GPT-2 tokenizer, which had a vocabulary of roughly 50,000 tokens, and it chops it up into 9 separate pieces. It splits transformer into transform and air.
Right.
But pass that exact same string to GPT-4, which boasts a 100,000 token vocabulary, and it keeps it intact as just 6 tokens. Here's where it gets really interesting. Vocabulary size is a direct lever for compute efficiency.
A larger vocabulary fundamentally compresses the sequence length. Fewer tokens to represent the same text means your context window can effectively hold more raw information.
Right.
More importantly, the model requires fewer computational steps to process the entire sequence, making it significantly cheaper and faster to run inference. It also helps the model track long-range dependencies because the information isn't spread across as many discrete steps.
But bigger isn't always better, especially when we step away from natural language and start throwing code and math at these tokenizers.
Oh, man. Yeah.
If you're building dev tools or agents, you hit these edge cases constantly. Tokenizers notoriously struggle with code formatting. Natural language has spaces. Code has variable names like get-to-profile data smashed together.
With underscores and camel case, yeah.
Worse, in languages like Python, whitespace indentation is literally syntax. But to a tokenizer, 4 spaces might just get compressed into a single token in weird, unpredictable ways depending on the training data. And math. Math is a complete nightmare for BPE.
Math is the perfect example of where greedy statistical merging actively destroys reasoning capabilities.
How so?
Take an arbitrary large number, like 31,415,926. To a human, that's a single numerical value. But to a standard BPE tokenizer, depending entirely on what digit sequences were popular in the training data, it might arbitrarily slice that string into 3 tokens, 314, 159, and 26.
The model has absolutely no idea that those chunks represent hundreds, thousands, or millions.
Exactly. It fundamentally breaks the positional alignment. Neural networks rely heavily on positional embeddings to understand relationships. If you tokenize one number into chunks of 3 digits and another number you want to add it to into chunks of 2, how does the network ever learn to carry the 1?
It can't align the columns.
Right. It renders the model mathematically blind.
This is why if you look at modern code-specific models like Codalama, they explicitly modify their tokenizer training to ensure things like a 4-space indent always map to a single consistent token.
Yeah.
And for math, many recent architectures force the tokenizer to split digits individually. So 314 becomes the array 314.
It's a deliberate engineering trade-off. By forcing single-digit tokens, you artificially inflate the token count and eat up more of your context window. But the payoff is that the model can finally perform arithmetic reasoning because it can clearly see and align the individual place values.
Which brings us to the actual infrastructure running all of this in production. Because if we're forcing digit splits and artificially inflating token counts, we need a way to process those tokens incredibly fast.
We do.
Tokenization isn't just an abstract concept, it is a massive CPU bottleneck when you're serving millions of requests. This is where tools like TikToken step in.
Okay, Token is great.
It's OpenAI's open-source Rust implementation of BPE. Because it's written in Rust and utilizes heavy caching, it runs something like 3 to 6 times faster than standard Python-based Hugging Face libraries.
It's just huge.
Yeah, if you are calculating API costs on the fly or chunking massive documents for a RAG pipeline, TikToken is essential. But when you dig into the source code of how it actually operates, you hit this concept of the merge table.
Merge table is essentially the compiled memory of the tokenizer. When the BPE algorithm finishes its initial training phase over the dataset, it outputs a strict chronological list of every single merge it performed, in exact order. First, it merged E and S, then E's and T, and so on. This table acts as a rigid compilation pipeline.
It's essentially a massive list of strict find and replace macros.
That's the right way to visualize it.
Yeah.
When you deploy the model and tokenize a new user prompt at inference time, you must apply those exact same find and replace macros in that exact sequence.
Or else.
Yeah, or else.
Or else.
If you deviate at all, the raw bytes will be grouped differently, generating completely different integer token IDs.
And this highlights an architectural absolute that every developer needs to understand before they start fine-tuning tokenizer selection is a one-way door. You cannot swap a tokenizer after a model has been trained, period.
It's a remarkably common misconception. Engineers will notice the model struggling with math and think, oh, I'll just swap in a better tokenizer that splits digits.
You can't do that.
No, you can't. The model's initial embedding layer maps specific integer token IDs to highly complex, learned mathematical vectors. In your original tokenizer, token ID 42 might map to the high-dimensional vector representing the concept of the. If you swap the tokenizer, token ID 42 might now represent XYZ or a snippet of Python code. You've suddenly scrambled the entire dictionary the neural net relies on. Changing the tokenizer post-training turns the entire multi-billion parameter model into complete gibberish.
You would have to train the model entirely from scratch.
Yep.
Which leads to the obvious frontier question. If tokenizers inflate cloud costs for non-English languages, if they mangle Python indents, if they break mathematical alignment, and if they lock us into an irreversible one-way door, why don't we just get rid of them entirely?
It's the most logical architectural evolution, honestly, and it's where significant research is focused right now, byte-level models.
Okay, what are those?
These are transformer architectures designed to bypass the tokenization pipeline completely and ingest the raw 0 to 255 byte stream directly.
That sounds perfect, but there's always a bottleneck.
Always. The bottleneck is the core mechanism of the transformer itself,
Right.
the attention mechanism. In a standard transformer, attention requires every single token in the sequence to calculate a relationship score with every other token.
Right.
The mathematical reality of that matrix multiplication is that it scales quadratically.
Meaning if you double the sequence length, the compute cost doesn't just double, it quadruples n-squared operations.
Precisely. Let's look at the math. A standard short sentence might compress down to roughly 25 tokens using BPE. But if you strip away the tokenizer and feed that same sentence in as raw bytes,
It's way longer.
it's about 100 bytes. Your input sequence is now 4 times longer. Because of that quadratic n-squared scaling, a 4x increase in sequence length makes the attention mechanism 16 times more computationally expensive to run.
Wow.
Yeah. For processing long documents or code bases, standard attention over raw bytes just becomes computationally impossible.
So to solve the tokenizer problem, we actually have to solve the quadratic attention problem first.
They are deeply intertwined. Researchers are attacking this from multiple angles right now. They're exploring byte-level transformers with local attention windows, where the model only calculates relationships with nearby bytes instead of the entire sequence. They're also testing byte-level patching, which uses a tiny, fast model to compress groups of raw bytes into dense vectors before feeding them to the main transformer. And there are hierarchical architectures like Megabyte, which process the raw bytes in small, isolated chunks and then analyze the outputs of those chunks globally.
So what does this all mean for the developer listening right now? It means for today, for the architecture you're deploying to production tomorrow, BPE is still the reigning champion.
It definitely is.
It is a brilliant, highly effective hack from the 1990s that makes modern AI economically feasible by keeping sequence lengths manageable, but its days might be numbered as compute efficiency and new architectures catch up.
It's a critical bridge technology. An elegant workaround, but a temporary one in the grand scheme of machine learning.
The next time you hit that API endpoint and wait for the JSON response, just remember before the neural network ever fires, you are triggering a massive cascade of statistical byte merges designed decades ago to shrink desktop files. It's a great reminder of how deeply layered and wonderfully messy our technology stack really is.
Couldn't agree more.
But I want to leave you with a final thought to mull over as you jump back into your code editors. We talked about how tokenizers limit the scope of what models can process, and how future architectures like Megabyte might successfully eliminate them, allowing models to natively read raw byte streams.
Right.
If that happens, does the language in large language model become obsolete? Will tomorrow's engineers be training foundational models natively on compiled.exe binaries, raw audio streams, and network packets, treating all of digital reality as just another sequence to be predicted? Think about it. Thanks for taking this deep dive with us tonight. Keep building, and we'll catch you on the next one.